Hi steel friends, we're going to do another example with yielding and fracture. This time we're going to do it with a double channel section, so it's a 2C10x20 member that's connected to a plate member and then ultimately transferring the load to another double channel member on the other side. Just so we orient ourselves to the problem, this is the top view, the second figure here. And you can kind of see then the two channel sections. So they're back-to-back channel sections that are our tension member. And then when we look at the side view, we can kind of see the details on the connection geometry. The member is both the channels and the plate are considered to be A36 steel for this problem. We have a bolt diameter of 3/4 inch for the design and standard holes as we talked about in class. In previous problems, we would figure out which member had the lower gross cross-sectional area because that's the one that's going to control for yielding. But for fracture, it's a lot harder to tell which one will necessarily control. When we have like two plate members connected, it's sometimes easy. But since these members are much different, I would suggest you check both capacities in both members for yielding and for fracture to figure out which one is the controlling limit state. Again, as for yielding, the lower gross cross-sectional area will control, so we are able to figure that out pretty easily. But for fracture, it's not going to be obvious because remember, fracture, the nominal fracture strength depends on the shear lag factor, U, as well as the net section area. For the plate, the splice plate in here, that U is going to be 1 because the entire plate is connected. But in the double channel section, we can see that only the web of the channels will be connected and we'll have the two flanges outstanding. And so that channel is going to have some sort of shear lag, so U is going to be less than 1. In addition, their net section areas could be different. So we do want to check both of these members for fracture. And we'll go ahead and do it for yielding too, just so we can kind of complete the design. So I'm just going to divide my page here and I'm just going to do the calculations for the double channel member on the left and for the plate 1x12 member on the right. And we'll start off with yielding. Yielding's a good place to get started, kind of gets our calculation rhythm going. It's one of the easier limit states to check. Alright, so we'll start with our general design equation. P sub u has to be less than or equal to phi pn. So P sub u for yielding has to be less than or equal to 0.90, because that's our phi factor for yielding, times Fy times Ag. So we recall that for A36 steel, Fy is 36 KSI. Ag for the double channel member, we're going to have to get this from part 1 in our manual. Now, part 1 has a section for double channels, but I tend to like to use the single channel section and then just multiply my answers by 2. So I'm here in table 1-5 to get these properties. So I found that for a channel 10x20 section, the gross area was 5.87 inches squared, and I'll multiply that by 2 to get 11.74 inches squared for the entire member. Alright, completing my calculations, that's going to give me P sub u is less than or equal to, I multiply 0.9 times 36 times 11.74 inches squared, and I get the answer that P sub u has to be less than or equal to 380 0.38 kips. Alright, I'll do the same for the PL1x12 member. So again, P sub u has to be less than or equal to phi pn. P sub u will be less than or equal to 0.90 FYAG. Fy for the plate member is also 36 KSI. Remember, we can have different materials for each of the different members in this case, and you would just use the appropriate yield stress. For the gross cross-section for a PL1x12, it's 1 inch by 12 inch, so that gives us 12 inches squared. There's only one of those plate members, so there's no multiplication here. So we take 12 inches squared times 36 KSI times 0.90, and we get that P sub u has to be less than or equal to 388.8 kips for the PL1x12 member. So at least in the limit state of yielding, the double channel section will control. Now let's move on to the limit state of fracture. So I'm going to go ahead and divide my calculations up again. For the double channel member, the 2C10x20 on the left-hand side, and I'll do my fracture calculations for the PL1x12 on the right-hand side. Alright, whenever we do the fracture calculations, we can start with our P sub u less than or equal to phi pn. P sub u has to be less than or equal to, remember phi for fracture is 0.75 times F sub u times AE. F sub u for an A36 steel is going to be 58 KSI. And now we have to come up with the effective area. The effective area is the shear lag factor U times the net section area. We look up for our double channel section. We find that it fits case 2 from table D 3.1. And the formula for U from that table is 1 minus x bar over L. And in the last lesson, we looked at how we come up with the shear lag factor for a channel section connected like it is in this example. For our net section area, we don't really know what this is yet, right? We know we have to reduce, we have to get rid of the bolt holes, but we'll have to consider a few fracture paths. As for the plate, we have kind of the same setup. P sub u has to be less than or equal to phi pn, so P sub u has to be less than or equal to 0.75 F sub u times AE. Fu equals 58 KSI. U, because the plate is just the single plate member connected, U is 1. So this fits case 1 from AISC table D 3.1. And then again, for our net section area of the plate, we don't really know this yet, and we'll have to consider fracture paths for what happens if the plate member were to fracture, and where is it likely to fracture. Alright, so let's start with the shear lag factor for the double channel section. So here's a quick sketch of the double channel section as it's connected to the plate member. I've sketched the plate member here with magenta and the double channel section in black. U is 1 minus x bar over L, and if we look at this, because the channel section, not all the elements of the cross section are connected to that plate, we have to consider the effect of the shear lag as, axial force in those flanges of the channel get back to the plate. And so to figure that out, we need to figure out the distance between the center of gravity of the channel section and the plane of the connection, because that is our definition for x bar. In this case, x bar is going to be 0.606 inches. We can actually get this from table 1-5 for the channel member. And in table 1-5, this will actually be x bar as it's listed in that table. L is the total length of the connection, and so we have to go back and look closely at the length of our connection. The length of our connection in a bolted connection is just from the first line of bolts to the back line of bolts. So for the channel member, from the first line of bolts to the back line of bolts, it's going to be 6 inches, or 2 horizontal spacings. So we'll use L equals 6 inches. Once we have X bar and L, the calculation for the shear lag factor is straightforward. We do 1 minus 0.606 inches over 6 inches, and this will give us a decimal about 0.90. Again, it's kind of standard to round U to the 100th place. Next, we have to figure out the net section area for the channel member. So let's take a look at the channel member and figure out what are some of the likely fracture paths that we would be expecting for this member. Again, as we move from the full load in the channel member, and as that full load is being distributed into the bolts, we would expect fracture at the front line of the connection. And so that's going to be this line that I'll sketch in green. The very first fracture path I like to consider is just full fracture right across the front edge of that channel member. So that's going to be through A, B, C, D. In addition to that, I recognize that maybe it would split on a diagonal and connect these other 2 bolt holes in the middle. So we'll give those bolt holes letters. Let's give them E and F, and then we go back to C and down to D. So I think these are the 2 main paths that I would think would control the design for this particular member. I'll sketch one more path because I like to be certain that I got all of them. There's the possibility, remember, whenever we go on a diagonal, we get to add a little bit extra to our net section area. So I'm going to consider the section in blue. The section in blue will go through 4 bolts in the cross section, across the width of the channel member there, the depth of the channel member. But it won't go on any diagonals. However, HJEFKM, that line lies behind 2 of the 10 bolt holes, so it's subjected to a lower load. So we're going to have to multiply kind of by that reciprocal fraction, 10/8, to compare it to the first 2 lines that we drew. So let's go ahead and figure out what our net section areas are. I'll set up my little table and I'll look at the different paths. Alright, so the first path was the path in green, A, B, C, D. And it just goes straight across the depth of the channel. And again, our formula for our net section area is the gross section area minus n times the diameter of the bolt plus 1/8 of an inch times the thickness plus the summation of s squared over 4g times t. So I want to look at path A, B, C, D. And we see that it passes through 2 bolt holes in the cross section. So we have the gross section area of the channel minus 2 times the 3/4 inch plus 1/8 inch times the thickness. Now we have to take a look, and remember that thickness is really the thickness of the plate piece where we've drilled the bolt. And so for the channel member, we're drilling that bolt hole through the web, and so the thickness that we need to use is going to be the thickness of the web, at least when we do our net section area calculations for the channel member. So we can look up the thickness of the web, and that's 0.379 inches. We can't forget that these calculations were done for just one channel member, so we have to multiply all of these results by the two channel members that we have for the double channel tension member. So when we do that, we take the total of what's in brackets there, we multiply it by the two shapes, and that gives us a total of 10.41 inches squared for net section area on path ABCD. Now remember, this is just one of the three paths we thought of for the channel member. So now we have to go back and explore the other two. So the next one we'll look at is the red path, ABEFCD. So again, for a single channel member, this is going to be 5.87 inches squared minus, we now go through 4 bolt holes. So we'll subtract out the 4 times 3/4 of an inch plus an 1/8 inch times the thickness of the web, 0.379 inches. But now we go on 2 diagonals, and so we have to add 2 times s squared over 4g times the thickness of the channel member, again 0.379 inches. So let's take a look at the geometry to get S and G. So S is the horizontal spacing, so in this particular diagonal that's going to be 3 inches, and G is the transverse spacing. In this case, both of those diagonals, G is going to be 2.5 inches. So I'll plug that into the equation that I had previously written down, 3 and 2.5. We do our calculations. Again, we multiply by 2 because it's a double channel member. So all of the bracketed results is just for the one channel, then we multiply that by 2. So our answer here is now 10.45 inches squared. So only slightly higher than path ABCD. So that basically means, like, right now we're expecting ABCD to be our critical path because it has the lowest net section area. Lastly, we said we would consider the line in blue, HJEFKM. So when we consider that line, we do 5.87 inches squared minus 4 times the 3/4 inch plus an 1/8 inch times 0.379. We have no diagonals for this particular path, so we don't add anything on top of that. Now, we do, however, see that for this path, the free body diagram that we would get is that area in blue that I've shaded in blue here. That area in blue is what's left, and that's subjected to 8/10 of the load because that area in blue contained 8 bolts. So we're going to multiply this by 10 over 8 so that we can compare it to the previous pass. Finally, we multiply it by 2 because we have 2 of these channel members for the overall tension member. This gives us 11.359 inches squared as our answer, and we see that this is higher than the previous two, so this path in blue will not be the critical path. We now can conclude that path ABCD will control the design for fracture here. And we can finish our fracture calculations now for the double channel member. So completing those calculations, we say P sub U has to be less than our phi factor, which is 0.75 for fracture. multiplied by the ultimate stress of the steel times the effective area, which is going to be the shear lag factor 0.90 times the lowest net section area, which was 10.4135 inches squared. We do our math. P sub u has to be less than or equal to 407.69 kips. And finally, we have to determine the fracture capacity for the plate PL1x12 member. The net section area is the only thing left to calculate for this particular member. And so we'll have to identify a path and calculate the net section area for those paths. So we'll go back to take a look at the connection geometry. So if we look at the connection geometry for the plate, where is the plate fully loaded? The plate member connecting these two is only fully loaded in the very middle between the two channel sections. So like going left to right, we pick up a little bit of load, a little bit more load, a little bit more load as we get to that third bolt line, and then we have the full load acting in the plate. And then as we keep moving left to right, the full load in the plate is now getting distributed back to the channel sections on the right at that first bolt line, at the second, and the third. So the most critical spot, like where we would expect yielding, would be in this middle zone for the plate. And then where we would expect fracture would be at the first bolt line, but relative to where the full load of the plate is. So that's going to be path 1 here. And we're going to go straight across here. I don't think we need to consider any of the diagonal paths, as none of those would control, because none of those would really result in more diameters in the width of the plate. So the only one we really need to check here is path 1. So path 1, we say the net section area is the gross section area minus the number of bolts in the width of the plate times the diameter of the bolts plus 1/8 of an inch times the thickness of the plate. So that's going to be 12 inches squared as the gross area minus path 1 went through 4 bolt holes, so minus 4 times the diameter of the bolt plus 1/8 of an inch, 3/4 plus 1/8 inch, times 1 inch thickness of the plate. No diagonals, so plus 0, so no s squared over 4g terms. And there's only one of these plate members, so we don't have to do the multiply by 2 trick again. So path 1 is now going to have a net section area of 8.5 inches squared. Alright, so that's the only path that we needed to check for this particular problem. And so now we're ready to finish our calculations for fracture. P sub u has to be less than or equal to 0.75 times 58 KSI times u, which is 1.0, times the net section area 8.5 inches squared. And that bracket there now is our effective area from our formula. So doing the math, P sub u has to be less than or equal to 369.75 kips. Alright, so now we have to take a look at the overall, what is the final capacity of this connection? Well, we go back, we look at yielding. For yielding in the channel members, we expected yielding at 380.83. For yielding in the plate, 388.8 kips. For fracture in the channels, 407.7. And for fracture in the plate, 369.75 kips. So we see that the lowest capacity is this 369.75 kips. We would say this controls the design. So the final phi-pn value for our connection, or just our final answer, our final strength, is going to be P sub U has to be less than 369.75 kips, so this member does not fail. Hope you enjoyed!